Hey, YouTube, how is it going? I hope all is well. Today, we're going to actually talk about what's going on with this guy here. I'm going to show you some stuff on the screen here in just a moment, but more or less, we're kind of just creating together. We're going to try to create, I guess, a schematic or something like that. I can't say for sure that this is one I'll actually use, but it is... you'll kind of get the idea. It's very akin to what I'll probably go with in one of the designs. I'm going to tell you right off the bat, do not just copy this and go and make it yourself. This is an untested schematic. It's just something that's come out of my brain, and whether it works or not is up for debate. So just with that kind of caveat out of the way, it's, you know, what do they call that? Caveat emptor. It's up to you to suss this out. For right now, we're just kind of seeing how I'm doing this and what I do. I guess you get what I mean. Anyway, moving on. So over to the screen. Here we can see I have a schematic kind of laid out. If you haven't already caught one of my earlier videos, go back and watch some of my earlier videos, and I think there's a thing in there. It's like building the world's best guitar, like it's like episode number 1, 2, or 3 or something like that. And I do show this software here. It is free. It is provided by DigiKey, and it is called Schemit. Basically, it's just a free software that you can use. You do have to sign up with DigiDesign or DigiKey, excuse me. Not DigiDesign. Anyway, yeah, you have to sign up with them and have an account and all that. Yes, you get to know my whole name. Oh boy. But it's actually a pretty cool software. It's one of the few ones that I've seen where it has all the tubes and stuff in there and has most of the stuff that people like you and I are more interested in. You can see I have kind of jumped ahead here. I more or less did this just to save on some time, because there is a bit of explaining to do about why I did certain things, and I'll show you kind of how I did that with another little mock thing underneath it. But this is just a rough bare bones thing. You can see I did fill in some values and kind of give you an idea of what some things are. But that's just kind of to give you an idea or a reference. This is kind of going to help you understand to learn how to read schematics and get an idea of what is going on with each part. You can also possibly notice, maybe you haven't yet, but the naming structure I have kind of done pretty well here. I didn't go through and tidy it up exactly, but as best as I can tell, it's correct. So let's do this first. I think it's kind of important. I generally build with the power supply section first. I kind of want to know where that stuff's going to lay out, which is unfortunate because I like putting the values of the components within the power section last in my numbering scheme. I don't know why. It's just a me thing. It really doesn't matter which way you name the components or value, you know, the R11, R12, C6, C7. It doesn't matter if this one's C1 and that one's C2, and then this one's R1 and that one's R2. And then you start the numbers up here. It really doesn't matter as long as you pick one or the other first. Really all these numbers are for, and letters and stuff like that, is just to make sure that when you're building a schematic and then you're putting it into something else, you know, that you're going to actually build, is that you actually know what that part is. That's really all it's there for, is for reference. So some of this is correct, some of this is not. This is a power input, you know, for this guy right here. Then I put an SMPS. This is an SMPS. This is an SMPS power supply, so switch mode power supply, and then it's got a couple voltage rails. I had to come up with a voltage source to connect all these things here. And then of course you can see this little block right there, the little Phoenix block. That's what this is here, obviously. And then there's two different power sources on here. There's one for the heaters, which you can kind of see here as 3 and 4, and then the power output for the B plus or HT, if you want to call it that, on 1 and 2. And I'm not even sure that's correct. It's not labeled as such on here. It doesn't say 1, 2, and 3 and 4, but on the bottom here, it's got ground, B plus, and then it's got 6.3 and then ground. So when you're looking at it like this, it is in this orientation here. So that's the way I left it. So obviously these two are going to go to the heaters. I haven't sussed out yet exactly how the grounding works on this. Obviously there's a ground for both the B plus and the heaters. I do not know if those need to go together or not, or if they even need to go to the chassis ground at all. I have not sussed that out. So again, I want to emphasize to you, do not just go and build this schematic here. Find yourself one of these and then connect it like I show right now. That may not be correct. This may actually be a local ground within this unit right here that is not meant to touch the chassis or any other part of the circuit. It may not. I do not know yet. That's what I need to find out. That's part of the testing I have to do. So as far as a normal schematic goes, going back to the screen here, this is more or less how you would draw it out. Depending on the grounding scheme that's required for these here, I may change these up to a different type of ground symbol, just to make sure that, you know, it's very obvious that, you know, this one and this one don't go together, and that this one and this one don't go together. That's that sort of thing. So moving on. All right, so we've got the little headers here that let us know that, I say headers, I did not say heaters. These things here just kind of let you know that this is a node. So you need to have a current resistor in line with this. Even though this does supply the voltage already, you need to assume that it does not have any current control on its output. So always put a resistor first. All this does right here is take, you know, current or amperage or whatever you want to call it, current draw, and turn it into heat. And it's kind of a way to just ensure that you don't have an inrush of current that's, you know, way too much for what you got going on. You still do have to use node decoupling capacitors and stuff like that in a device like this. So just because this thing does produce, you know, a regulated or semi-regulated 250 volt output does not mean that it is ready to just connect straight to your you know, to your tubes or whatever else you're connecting to. You still need to have a proper power supply for it. So now we've got that out of the way. What values would I go with for these? I would start at 10K here and then go lower if you need it. There's very, very little current draw on this right now. So on this B plus rail, there's probably only 2, maybe 2 milliamps, if that, worth of current draw. So 2 milliamps going through a 10K resistor might only drop a few volts. It's not a whole heck of a lot of voltage drop, I can tell you that right now. So you may need to even go larger if you want to get a larger voltage drop. Uncontrolled, I don't know exactly what the, you know, current draw on this thing is going to do in terms of voltage drop. So with a device like this where it is voltage driven, again, just a reminder, this thing is exchanging current or amperage or whatever you want to call it for voltage. So we're putting a very small voltage in that has higher levels of current available, and on the other end we're getting a large voltage out with a lower amount of current available. I believe this thing is rated for a little over an amp or something like that. I can't remember exactly off the top of my head. I'd have to check that out. But let's say it's rated for 1 amp at the B plus on this thing. Well, what does that mean for the input? Do you need to have 2 amps? Do you need to have 1 amp? What is that? My assumption, or my understanding of this particular unit here, is that it's pretty much 1-to-1. You put in a 500 milliamp power supply and you get about 500 milliamps worth of draw on the other side. 500 milliamps is honestly just about enough. The heaters in this circuit draw 6.3 volts. Well, we have 9 volts here, so it goes a little bit different in the other way. So the way that they do it with having 2 different power rails on here is that the high current side of things, which is the heaters that draw at 6.3 volts, right? you can convert the other way with it. So you can put a 500 millivolt power in and still get the amperage that you need to drive the high current stuff on the other side that is lower voltage. I think this thing accepts 9 to 12 volts. I'd have to double check, but not all of them do. Some of them don't, some of them do, right? But that's what allows you to get away with the current on the heaters for this, is that, again, the 6.3 volts is a higher current draw, but it's lower than the supply voltage, which means that within this thing here, there is a conversion that goes on that allows it to make up for the current that's needed, even though the power supply has a lower amount of available current. Does that make sense? I hope it does. So on the B plus side, the side that's got 250 some odd volts, well, we're only pulling maybe 2 milliamps out of that. Right? So this can easily punch up the voltage that high, even with a very low power source or very low wall wart power source, you know what I mean? And drive it still, because there is no current draw, or very minimal current draw on the high voltage side. So going back to the tubes heaters again, those draw about 300 milliamps a piece. So each tube draws about 300 milliamps. If we run it in parallel at 12 volts, or excuse me, yeah, parallel at 12 volts, I think it drops down to half of that amount, so about 300 milliamps for both of them. But it's a little bit noisier that way, I believe. I don't usually do it that way, so I'm not 100% familiar with exactly how it works out. But so 300 plus 300 is 600 milliamps. Well, that's only a 100 milliamp difference from this, the average power supply that you're going to have. Most power supplies range somewhere between, I'd say on the low end, maybe 250 milliamps up to about an amp or 1 amp. And I'm talking literally about those one spot, bricks that you can buy to put in, to power your pedals or whatnot. I have several D'Addario ones, or however that name is pronounced, that are 500 milliamps, and they seem to just love to power whatever you can plug into them. You can string as many as you want, and they seem to be noise free. But 500 milliamps worth of current source from the wall wart is enough to power this in its state for this circuit here that we're talking about. I apologize if I lost you there, but I hope that makes sense. I was trying to explain how this thing can get away with doing that, even though you're only using like a 9 volt power, wall wart power source that's only rated at 500 milliamps. That's how it can do it. It's all about conversion of current into power or voltage, and vice versa. So you just have to remember that relationship. If you have a low voltage source and you want a high voltage, supply, you're converting current into voltage, and vice versa. If you have a very, very high voltage on this side and you want to convert it into a lower voltage on the other end, even though this side here might have a very low current ability, so maybe it can only supply 1 amp, but it's 250 volts at 1 amp. Well, on this side over here, you're going to get 10 volts at several amps of current, right? Capability. So that's the exchange that goes on, and that's what a transformer does. A switch mode power supply does it a little bit differently. There, I think I beat that dead horse. I hope that makes some sense. So in my schematic here, you can see that I have this power jack here listed in there. It's shown there. And then I put SMPS. That's all we need to know, is that there's a switch mode power supply in there, right? And then I got 2 different voltage sources, and I noted them here. And then I, put these 2 here are the heaters, and these obviously go out this way. So now that we've kind of gotten back to where we started, let's move on. So I do plan on having 2 nodes at the very least. For right now, I'm going to keep it simple and plan on just 2 tubes. I am not, like I said, a fan of cathode followers. And I very, very, very much mean that I am not a fan of cathode followers. I am going to try my darndest to make a circuit like this that has a cathode follower in it as one of the options. that's basically a Marshall or a Vox or some Fenders, some options like that. But we're trying to do this into a pedal or a preamp. Now, you would think, well, why don't you put a full tone stack in there? That's great. I could do that. And you know what? I probably should do that. But I am not everyone else, and I'm not trying to be anyone else. So this is going to kind of be for me, I'm talking about me now. This is going to more or less be how I like to do things. So, like I say, don't necessarily just copy what I'm doing and run with it. Be original. Try to find something that works for you. If you want to put a full normal tone stack right here or right here, by all means, please do so. This is just a building block for me, and if I were going to do this circuit at this way, this is how I would do it. Now, I've already mentioned before, I am kind of a fan of the parallel triode thing. I did that in this schematic here. So you can kind of see here that this one is tied together on what would be pins 2 and 7, excuse me. So I did that, and of course pins 1 and 6 are tied together, and then the cathodes, 3 and 8 are tied together. So just be mindful of that. That's why I put VA plus V1A plus V1B. I'm going to give that a shot in this particular pedal. We'll see how I feel about it. I wasn't necessarily anticipating purposely doing that in some of the other designs. I'm going to have to split this up and run like a more normal type of giddy up. I thought about it for a brief moment of splitting these up and making it just two more, an extra gain stage here, so there'd be, 2 gain stages, if you will. But I decided I was going to keep it simple and do what I said I was going to do, and kind of make like a plexi / AC30 type circuit. That's what this is. This is probably most akin to what would be a Vox AC30 kind of thing. The plexi does kind of have the same layout. Now, where I do it different, and because this is also realistically going to be a pedal, I put the tone later in the circuit, and I put my normal low cut circuit. This is kind of my low cut circuit here. It's not original, don't get me wrong, but there are not any modern companies other than myself that I know of that is doing that. Matchless has a slightly different variation of it, etc., etc. But moving on, you can see here I have labeled the input and the output. I did not show the switching in this, so it does not have any kind of thing for a switch of a boost. It doesn't have anything to even switch the pedal in and out. That will be added, but for simplicity and just getting through this whole process, here we are. Okay, so you always have to have, especially with tubes, a reference to ground, and that's what this is. This is basically going to be your 1 meg. So I'm going to right here put 1M. It's not an A, but we're going to put 1M. So 1 meg is the value. This guy here, it really doesn't matter which value you use. You just need to have one. I prefer 10K. That is a me thing. You can put anything you want. So when you parallel the tubes like this, you double up on the Miller capacitance that they have. Read up on it. I'm not going to go there. But basically, when you double up on the Miller capacitance, you basically need to have half the value that you would normally have here. Fender is known for using 68K, but then they put two 68Ks in parallel because the way they do most of their inputs, their high and their low inputs, which realistically adds up to about 33K, right? Somewhere in there, 33 point something K. I believe, under my understanding, that about 20 to 22K is all that is required for a standard one single triode value in order to do what it needs to do for the purpose that this is here for, which is to keep Radio Disney from getting into your amplifier and being amplified, or in this case, your preamp and being amplified. So you don't have to go very high, and in this case here, because I have two of them together, triodes that is, I can then have it again and go to 10K. I like going lower if I can. It does help make the amp or that channel, whatever it is that it's connected to, a little bit brighter. So you can go as low as you want. You don't necessarily have to have it. But if you're going to do a high gain circuit, something that's got considerably more gain than this one, you're probably going to wish you did go a little bit higher in value. 68K is popular for a reason, especially with higher gain circuits. It's more or less because you've got so much gain going through the amp that you really have to make sure that you get the noise out of, you want to keep Radio Disney from being amplified through this thing. The other thing that you must note is that this thing here, in order for it to be truly effective at doing what its primary goal is, it needs to be connected directly to the pin. And when I say directly to the pin, going back to my hands here, my grimy ass hands, we're talking literally to the pin of the tube. So one of these pins right there is where it would go, and this other pin over here on the other side is where it would go. So just note that when you put those on in your own design and when you're doing your layouts and your builds, try to get the grid stoppers on the pin of the tube. All right, enough with that. So as far as these values here, you can go with whatever values you really like. Anything between 2.7 all the way down to as low as 420 ohms would work just fine. I am not super duper crazy about trying to eke every amount of possible gain out of this channel as I can, so I'm okay, and I generally tend to land right about 1.5 kilohertz or kilo ohms, not kilohertz, excuse me. As far as gain goes, again, we talked about this in other videos for the plate resistors. With a parallel triode like this, generally you have the values, so 1.5K kind of being center biased, you would generally go with something like a 750 ohm or something like that, right? And then up here, you wouldn't go up in value, you'd actually cut it in half. So if 100K is generally what you would have, somewhere between 50 and 68K is normally what you would have. I like using 100K. It tends to work pretty well. It's not overly gainy, and it's not so high that it makes it sterile sounding. It's still kind of got that bubbliness to it. When you go lower in value, closer to 50K, it starts to get very, very fendery, which is nice, but you also kind of lose a lot of the benefits of doing this kind of circuit here, which is to add just a little bit more gain. I'm kind of giving you all the secrets here, but you get a little bit more gain when you do a parallel triode than you would just a single triode. Just a little bit, not a whole lot. It's not markedly different, but going with 100K, even though it's double the, standard, plate value that you would go with for that setup, it doesn't really react the same as if you did it with just a single triode. So there is that. Now, this is my little low cut circuit. I've talked about it before. It's not a huge secret, but nobody's really doing it, so don't you do it. It's for me. More or less the way I do it is this is my primary one here, and that one is going to be a very low value, somewhere between 250 PF, and actually I did that wrong, it was PF, up to 500 PF. And then this guy here is actually the big one that you would use, which can be 0.022 if you wanted to do that. And we'll go UF. And of course it's going to be up there, because why wouldn't it be, right? So we'll get this guy down, I don't know, there. We'll put it there. It doesn't really matter what values you pick. You just have to have them in the right orientation. You just got to know that this one here is circumventing the potentiometer here, and because it circumvents the potentiometer, this one is always in circuit, and what you're essentially doing is adding this value over the top of it in parallel, and because it's in parallel, these two will add up together in value. That's why I use a fairly large value here for the the pot. Some people would argue that it adds noise. I have not seemed to have much of a problem. More because by the time you get it churned down to where this thing is out of the circuit, pretty much, there's enough signal going around over the top of it that you can't even tell that none of the shot noise coming from the resistor in the potentiometer is doing anything. So I haven't noticed any big problems with it. I think you get more noise out of this guy here, honestly, because it's literally in the path. When this thing is all the way up, that resistor is out of the circuit at that point, so you don't really hear it. That's just a me thing. You can experiment with these values. Going to the drive, standard 1 meg, might not need to be that high. It might need to be that high. We do not know. I do not know at these voltages if we're going to have any kind of problems with blocking distortion. I can tell you right now that one parallel triode going into a single gain stage will cause this thing to break up pretty good. Enough so that with a 1 meg audio taper pot, you can get into blocking distortion. So there may be another circuit in here, I do not know, which will consist of a grid stopper with perhaps, we do not know yet, but perhaps a treble bleed that goes over the top of that. There's all kinds of different ways you can do it. We do not know yet. So just, I have space in here that we can put that in if we need to. So going on to this guy here, I pretty much anticipate being at a 100K. So we'll put 100K. It's a standard value, nothing crazy about it. This guy here is also generally 100K, although it can be just about any value you wish. If you go and you look at different schematics that have a cathode follower, it ranges anywhere from 56K all the way up to 100K. The higher the value, the more gain you are going to get out of the remaining portion of this circuit. So I would probably, considering the fact that we're going to be using this in a pedal format, and where then the next pedal in line can't probably actually take the voltage that will be produced by this point in time, or the current for that matter, I would probably be more focused on going lower in value. So I'm going to put 56K just out of safety. This one here is your standard values. You can put 820 ohm, you can put 1.5K. Generally, it's pretty hot though. It's usually closer to 820 ohms, so that's what we will put. And I don't have, I'm just gonna put 820, we'll leave it simple. Now, a boost circuit that you could do in this particular amp here would be to put a bypass cap around this guy here. Some amps do it, some amps don't. This is low gain enough that you can get away with putting one here, and it would do kind of what you expect it to do, which is add more gain and girth and grit and all that fun stuff. I did not show it here because I do not know for sure where we are going to sit yet. I can tell you that this guy here will distort, and it may actually be the first thing in this circuit that does. When I say this thing here, I'm talking the cathode follower. I opted to go with this configuration here. There's a couple different ways you can do it. This is kind of the simpler one, but more or less this is just a standard, high cut type circuit. So here we can do basically a standard value potentiometer. So we'll put a 0.022 just because we can. So we'll go U and F. This one here, it really doesn't matter what size you use. I would say that, how do you want to put it? In this case here, you can do 0.0047 if you want. You can do 0.0022 if you want, or you can even do 0.1 if you want. It kind of, the value of this pot is really what kind of drives the size of the potential, or the cap that you use. So if you use a larger value cap, you kind of need to use a higher value here, because 100K is going to bleed quite a bit of signal off. I'm purposely using a lower value here to help drive some signal down. Part of the reason why I decided to go with this cathode follower design first. So with 100K, I would assume something like this. We're going to start with a hypothetical value of 0.047 UF. That is a me thing. I don't know. And now I'm also using a 100K volume pot for the output. Again, I'm going with a lower value to make sure that it is not so much gain coming out of here that it's just going to destroy whatever's next in line. You got to think about the voltage gain that you get as you go through the number of stages that you have, especially with the voltage on the rail that you, goodness gracious, on the rail that you have. So you come in here with a couple millivolts, you know, maybe 50 tops or something like that. Well, on the output of this thing here, depending on how you have the low cut set, you might get anywhere as high as 6 to 10 volts, depending on your HT, right? So 6 to 10 volts is a lot. 6 volts is plenty. Well, 6 volts coming out of this guy here is going to spank the ever-living crap out of this guy here. All the beans are coming, right? So you can probably get, it's not quite a 10x. I'm not going to get into the mathematics of it. That's what the mu of the tube is all about. A 12AX7 is like a 100 mu. Realistically, you're only getting 50 to 60 out of it. And that's to say that it's 50 to 60x the amount of gain that comes out. No, that does not mean if you put 1 volt in, you're going to get 60 volts out. It could be around there, though. So if you're putting 6 volts in, and maybe not because you got the volume control there, but let's say you're getting 6 volts in, it's not unfathomable to imagine that you're going to have 20 to as much as 60 volts out, right? That's not uncommon. And then of course you're going yet through another gain stage. Now the beautiful thing about this one, a beautiful thing about this one is that it is exchanging current or voltage for current. So on this output with this particular setup here, it will not have as much voltage, but it will have plenty of current to drive through all this. We're hoping that using a 100K pot will knock it down enough that even at nominal levels, normal volumes, it's not, just gonna blast the ever-living crap out of the next thing in line. We'll see. We don't know exactly. I've tried looking at a few other pedal designs, and not all of them are very clear on exactly how they do it. Mainly because, you got the tube driver, the BK Butler tube driver or something like that. You got the Matsumin. All of them kind of run like normal circuits. And these are kind of the standard values they have. Some of them have 10K pots, some of them have 100K. Really just kind of depends. I want to get away from using transformers, although using transformers in here would probably be the better way to go. With the transformers, I can get the outputs and or the inputs isolated so that it's not a direct voltage coupled thing to the next stage. Whatever other pedals that you got in there. Do keep in mind that that's what the capacitors are here for. Those do keep the DC volts out of the next stage. It probably would behoove me to put one here as well in the front end. There's a couple amps out there that do it. If I'm not mistaken, the Tiny Terror, the orange Tiny Terror, I believe, has a little .022 in the front end. And when they were asking him about it and what it does, the general consensus was that it was for protection against DC from the preceding effect. But honestly, I think he was doing it more to control low end getting into the amp. So you do get a low roll off when you put a capacitor, literally right in this spot right here. And then you put that 1 meg, that creates a low roll off. And with .022, which is I think the value that they use in the micro tear or the tiny tear or whatever the heck it is, it's right around 80 hertz. So it's right around the ideal frequency for a normal guitar with standard tuning. So it's just to help control bass, but I think it also has the added benefit of making sure that no DC is getting into the grids of that first tube. But whatever. Moving on. So there's a couple things, as I had already mentioned, that are not in here that may need to go in here. I'm hoping not to use transformers because transformers are expensive. I don't use cheap crap, and the transformers that I would use are Leles. Lele's or Lele's. I don't know how you pronounce it, but it's Lelhe or something like that. Whatever it is, or Lehle or something. But Lele. They are about $70 a pop, and I would probably use one at least, but possibly might need two. And if you can imagine, $140 worth of that's before shipping, by the way, of transformers sitting in here. I mean, just the transformers alone would cost more than all the parts and everything else that's in it. So it gets real expensive really quick. These are not expensive. Going back to my hand here. These things here are not crazy expensive. This one is a test bed. So if it works with this, I will try to retrace this circuit out and redo another one that is of higher quality and is designed to fit onto something else that I utilize, because I'm cool like that. But let's actually show you how you would do this if you were to have this program. So let's scroll up just a little bit. So I'm not going to worry about the naming so much, the values. It should start over, at the next highest value, but we'll see. I don't know. So again, I usually start with the power supply. So you're just going to have to come up with whatever power supply you want to use. Let's see here. Get in there. There. Darn it. There we go. Okay. So there's our power in, right? So you start with something that is whatever, power. And then you put in your... we're just going to pretend that we're not going to bother with this guy here. But so obviously that you need to have things connected to it. So you're going to go ahead and do the resistor first, and then we can rotate that to the direction we need it. You know that you're going to need a capacitor, and then you're going to need another resistor. And again, I mentioned that I go with the power supply first, and if you wouldn't mind, thank you. So I always start with the power supply first, and what I normally do is just throw it out onto the thing. I just want to know where everything's going to be. So there we go. We got our two nodes, and we've got a power supply. Yay! All right, so we also know that we have our heaters. So let's just go ahead and put some headers out there, or voltage rail things. So we know that we're going to have one here. It's probably just easier to copy and paste. By the way, it's easier to copy and paste things if we're going to do it this way. So here, we'll just do this, Control C, and it works the same as anything else, Control V. Yay, what do you know? And then we're going to rotate that. R on here does the rotate. I does the focus in. O focuses out. There's a couple quick keys. Once you learn them, it's pretty cool. So there you go. So now we know that we've got that. Now let's get some grounds out, because we know we're going to need those as well. So we're going to go here. We're going to go... And we know that we're going to need that again, so we'll go Control C, Control V, yay. So you can see how you can move around real quick. And then the arrow, move them around for the selected part. All right, so I don't have as much space as I'd like, so let's just do this. We're going to move this down just a little bit. So you saw there how I click to drag over all the things that I have selected that I want to use, right? Cool, makes sense. We're not going to imagine that we're trying to build any kind of power supply here, but normally you would put like a fuse or something like that in there. So let's just do that. We'll put a fuse there. What else might you have there? A diode. You generally have like a diode string for some of this stuff. So we'll, it's just being stubborn. I'm going too fast, apparently. Maybe, I don't know, whatever. There we go. All right, so there's our diode. We'll rotate that around. Cool. We're going to pretend that that's our power supply, and then you connect the dots by literally connecting the dots. It's pretty much that simple. Nothing crazy about it. So I'm going to move that out, and then you just literally find the spot here and click and drag it over there. And you can move these around afterwards, and it will sort of do a thing for you. So there is that. Let's take this, we'll move it there. Sorry if I'm going a little fast. I'm just trying to show you kind of how this would work. And you can almost do it this fast in real time if you really, really want. So you do have to kind of plan ahead when you're connecting these dots here. Once you connect the dots, I don't know that you can just draw another one. It gets kind of crazy. Like if you do this, it'll just do some weird stuff. I think it will allow you to run out of the middle. Yeah, you can do stupid stuff like that, but it's not very intuitive. So I find that the easiest way is to just kind of plan ahead and find where you want all your stuff to be, and then you can combine them as needed like that. So it creates all the stuff that you need to create, yada, 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 right? It is helpful to try to find a grid line that you are comfortable working with. And it's just to make things so that everything is consistent. So you can kind of see here, like everything's kind of on one little grid line. And this one actually needs to come down one, right? So now they're all on the same grid line. Well, same here. You want things to kind of be in line. You want it to try to look pretty, and you want to try to maintain at least some sort of consistency in space. So what we're going to do here is go like this and go like that. We'll move this guy down and over. Up 1, over 2, 3. All right. Yay, right? And is that, yep, it is. Click. There, now we got all that. I didn't put anything for ground, so we're just going to pretend that, let's do this here. So we got chassis ground here, right? Chassis ground, I said. So this is going to be chassis ground, and we're going to just do that. Get in there, if you wouldn't mind. There we go. Cool. There's chassis ground. We're going to just imagine that this goes there as well. Cool story, bro. We're going to pretend like this is going to our ground source over here. So then what we're going to do is go like this. Do imagine that these will fall in different spots. You do not have to connect them like I did here. So you could go like this, let's say, and you could delete this one even if you wanted, and then just put this down there. So you can just put this like that and then connect it. And you can do the same for this. You don't have to do the thing like I did there. The only reason I did that there is because I know that the voltage source is the same all the way around, so it can't possibly be different. So that's the only reason I connected them like that. All right, so you do something like that. Cool. All right, same for here. And now what you want to do is go through and kind of make note of what is what. So let's say we want this one to be A. So we're just going to put it, no, we need it to be a different letter. It won't let you rename the same thing. Well, actually it will, but whatever. We're doing this here, so we're going to call it C. And then you want to tell it to be that. And then you can move that letter around to suit your needs. And then this one here will be D, because why not? D. All right. There it is. Okay, cool. So now we've created our little power supply, right? Let's create like a half-assed circuit here. So we're just going to do a single triode. Thank you. We need an input, so we'll move that over. Let's get our input here. Thank you. We know that we need our resistor to ground, and this is how I try to build it out here. So when I'm building it out, I try to think of the signal of the circuit itself. So we know that this is our hot, so I'm going to, place this in here somewhere. This is our grid leak or our grid reference, however you want to call it. And then this one will be our actual, it's so stubborn. There we go. Click and dragging sometimes helps. So R, again, rotates things, and then again, just making sure it's on the same plane. And then you do the same thing with this one here for the grid, right? So we're gonna move it just a little bit closer, right? This guy will go to here. This guy will go to here. We know that we need a plate resistor, so we're gonna, sorry, my apologies here. So we're gonna drag a plate resistor out. We also know that we need a cathode resistor, so we'll grab a cathode resistor out. We're gonna pretend that we're going to bypass that. So we've got those now. I don't like how it's done that way, so let's do flip horizontally. So if you right click on these, you can get some different options here, and you can kind of see what the quick keys are. I don't always trust these ones. But anyway, so let's do this here. We're gonna take these ones and we're just gonna move them down a little bit, a little closer than I like them to be. All right, so I wish they kind of made them more the same size, but whatever, they don't. So that's just kind of how it is. So cool, we're gonna connect our cathode together here, and we're gonna take this guy and move it into its space, and then we're gonna go click like that. And then this is where you have to think ahead. So remember I was talking about how once you click on these things, it's really difficult to get a new line to come out. So here's what I found is kind of a cool trick to do that. So for your input, since you want it to be a grounding input, you do that. Now you've made that connection there. This one here is the end of this circuit. We're not using anything else in this circuit anymore. So you just kind of go down, out, and over. And then when you want it to kick a new direction, you left click, and that will give you a new direction that you can play with. And then you do that. So now you've got a whole circuit kind of surrounded there, which will allow you to play around and do stuff like this. And then you can conjoin everything. And conjoin everything, right? Great. Now we want another ground here. So we'll go click, drag that up into, that looks about right actually. And then we'll drag that up into there. There, now we have a full, almost a full circuit there. Let's take this and drag it down to our plate. We're gonna need another one of these. And since it's gonna be our C node, we're gonna Control C, Control V, and then we'll move it into place where we need it and click and drag that down. Yay, now we have that much done. We know that we need a coupling cap. So let's find a coupling cap here. Oh, by the way, I've been dragging over here from my favorites. So I have this is the library of favorites. So when you're in here, you'll have to go through the, most of the stuff that you're gonna need is in the schematic symbols. And you kind of got to think about what the part actually is. If it's an optoelectronic, so that's going to be like a LDR or something like that. A port would be something like this here. And then you got sensors, you got sources. This would be kind of a source right here. Motors, of course, diodes, everything kind of makes sense in that regard, right? So a lot of the things, vacuum tubes, some of this stuff kind of makes sense, some of it doesn't, switches, etc., etc. Passives, as you can tell, are going to be passive parts, so capacitors, inductors, and resistors. And if you go over here, you can see which ones I have clicked that I want to be, in my, favorites. So that's how you find those guys. So anyway, go through each of these things here and you'll kind of see all the different things. But once you build a user library, it's really helpful because then it makes it a lot easier to kind of get through and find what you want. So I need a coupling cap, and then we'll rotate that guy around, and it needs to be down here a little bit, and we'll move it out a little bit, and then we'll connect it to there. So we've almost completed our first whole circuit here for that. We know that we need a volume control, so let's go up to our variable resistor here. We'll take a volume control, put it there, because why not? And let's move it down so it's in line with that guy. One more up. All right, same, click and drag, right click, or left click, excuse me, gets you the option to move the line a different direction. We need another tube. So let's find another triode here and click. We'll put that there. It's probably going to need to move out a little bit. Let's just pretend we're going to put another grid stop on there. So we'll just put So we'll drag one of those out, rotate that around, and get it where we want. Yeah, right there. Sure, why not? All right, so we're going to do and right and bloop. And then this will go to the triode, and let's just finish out this other half of the circuit here, and then we'll kind of leave things alone. We'll kind of call it there, I guess, if you will. So we're going to just connect this one. I'm not going to bypass that one, so we're just going to go ahead and come around like this. And remember when I was talking about how coupling caps is the end of one circuit and the beginning of another, and that's why I'm encapsulating this one here. If you can imagine, by the time we get another resistor out here, it's going to be not on the same circuit, right? So we're going to put this guy here, and we're going to rotate that around. I said rotate, thank you. So, right, we connect that there. This here is not in this circuit any longer. So it breaks here. So we only worry about what's in this circuit here for this. So we'll go Control C, come over to here, we'll go Control V, and move that into position. And I want to make sure I'm on the right plane. I am. Looks like we're pretty well centered, and we'll call it a day. I shoot for as much symmetry as I can. It looks like it's one dot off, whatever. Okay, so there we go. We've built a complete circuit with the exception of this guy here. We'll go Control C, Control V, and we'll move him into place. Looks like we need to go up one more there. Looks like maybe this was down in the wrong spot. There we go. I like that. That works. Click. There we go. Now we have two complete triodes here, circuited up, all ready to go. This one got moved down one. I blew it. I so totally blew it. Let's see if I can get it to go up. Blam. There it is. And then that means that one's correct. Okay, cool. All right. Sorry. I squirreled. All right. So this one here, let's go ahead and move that up. There we go. Even though it's not on the right plane. Maybe I'm off. I don't know. Whatever. It was down one. You know what? Let's just keep it simple on ourselves. Because I can't help myself. Everything's got to be correct. Click. There we go. All right. I'm happy now. So then you just go through and you can go, so we started at R12 and then you can see there was an R13 somewhere, or R14 or whatever, right? This one here, you can put a little note. It says heaters. So you'll put heaters, click and blink. And then you can put this here. So that way you know that that goes to the heaters, right? And then you got your C node, your D node, etc., etc. The numbering of these, it doesn't really matter, but whether you do 18 or 19 or 19 and 18, it doesn't matter for these. It's just, again, it's just to make sure that you know in order. And it's best to make sure that you get them to kind of go in an order. So if you're going to call this one R4, or excuse me, if you're going to call this one R3 and this one R4, you need to go R7 and R8. You want it to have the same relative thing. You don't want to switch it up halfway through and go one direction and then the other direction. It helps you and it helps the next guy that's going to watch you do this stuff or, you know, try to build this crap. So R16, 17, 18, 19. We've got R20, 21. And then see here how I flipped them? It was the wrong way, right? So now we need to think about changing that, and I usually just add a number to the back side of it to make it easier. So I can come over to here and go R22, and then I can come back and go to this one and go R23. All right, there you go. So now it's in the right order. And then same thing goes for the capacitors, right? So I usually do these ones last, but if this one is C11, or this one is C10, this one's the next one in order, that would be C11, this would be C12, and then I guess it would make sense to make this one C13, and then this one C14. Now, again, it does not matter what direction you go, just so long as you pick a direction. If you want to start with the power supply first and make it 1 through whatever here, you can do that. I think a lot of companies do. I don't know, not all. But I like having the actual signal path start at 1 and then end with the power supply, even though I build the power supply first. Darn it. Yeah, you know, you get it. So there you have it. So now we've created, you know, a gain stage or an input gain stage and a proceeding gain stage, whatever you want to call it. I don't know. So there we have it. That is that. Obviously you can get more technical down here and pick the right components. I was just trying to show you as fast as I could how to build these sort of things here. The heaters, I don't bother trying to connect them in. I know that they're the heaters, so I don't bother with them. That is the heater, that is the heater. There's no mistaking that those are the heaters. So I just leave it alone and put the little pin there because you should probably know what the heaters are. So I hope that kind of makes sense what we just did there. Let's see, what's that going to select? That's going to select all that. So I'm going to delete this. Sorry, everybody. We don't need this anymore. So I'm going to go ahead and delete those. Ta-da. So that is it. I hope this answers some questions. about how to build a schematic, go ahead, like I say, go to DigiKey, find Scheme It, sign in or create an account, sign into DigiKey, Scheme It, and do your thing. Now, let's come back off the screen here for a second and get back to my dirty ass hands. So, that circuit is going to fit on here. I'm not certain yet how it's going to work. I am going to use not as contemporary parts for this, so I will use the axially or the radially mounted parts for this. And I think it's mostly just going to be so that way if I do mount them on this side here, it's sticking up a little bit less, and it's going to be where the tube is anyway. I would like to put them down here, but by the time I put I think realistically I should probably use at least a 22 UF for each of these nodes here. I'm going back to the screen again. A 22 UF, I didn't put a value there, but a 47 UF would probably be a little bit wiser of an idea. It'll make it pretty stiff, but there isn't any sag in the preamp of an amp anyway. The only reason that the values are what they are is that by the time you get to them, they're already very well filtered. So by the time you get to the very first tube, and I actually did this backwards, very much backwards. Hold on, let me correct that. So let me put C here, and you're going to see why it's backwards in just a moment. Talking of filtering, so this one needs to be B, and then this one needs to be A. Dang it, come on now, select, dang it, it's gonna make me work. All right, A. Okay, so why did I do that wrong? The lowest amount of filtering here, so it's, the very first node, if you will, in this is the later part of the circuit. So that actually needs to be A, and then B is the most filtered portion of the circuit, and it is also the lowest voltage because it's gone through 2 voltage drops at least, or 2 dropping resistors at least, which means that it needs to be the first tube. So this one would be B. Your very, very first tube is almost always your very, very last node. So if you have A, B, C, D, let's say you have 4 nodes and you end on D, or if you want to call it node 4, whatever, that one will be the one that goes to your very first tube in your circuit, your very first preamp tube. So again, just kind of going on about what happens when you go too fast. Do not just take any schematic that you see on the web and start running with it. Verify, verify, verify. Always verify. Because stupid little mistakes like that, in this case, it wouldn't hurt anything. It's just that I wouldn't have the right voltages that I want, and it might be noisier just because, I got the least filtered thing very first in the circuit, amplifying all that noise, which is just going to be even more amplified by the next stage. All right, so going back to here. Again, putting a 22 UF capacitor in here that is, axially mounted, that, lays down. It's about the size of my finger. You can imagine it's going to take up a lot of space down there. And I don't want to have this thing sitting, 5 inches. I don't want it sitting all the way up off the ground too much. I want to try to get it as tight to the thing as I can. And I think the only way around that is to probably drill some extra holes in here and put some extra turrets, so I can put a normally mounted, or an radial. It's a radial mounted capacitor here, and I will use more like the Nishikons or something like that, which have much better ratings anyway than those FNTs, and are smaller in size for the same voltage and same capacitance. So I'll put them here, drill a couple new holes, and then with that I'll be able to run wires and just all that kind of jizzy jazz. You know what I mean? You get it. All right, I think it's safe to say that I've kind of beat this horse to death. You get the idea. we're going to try to build all this onto that soon, or all that onto this. You know what I mean. I still need to do some testing with this, but I figure the next episode that we catch with me will probably be me actually populating this thing and starting that process. I'm not scared at the moment. This thing is literally going to be prototyping. The end product will not be made on this product here. I'll probably either make a custom board and drill all the holes that I need for it on that and do it that way. Or I will create a PCB board. I'm saying the word PCB. You know that I don't like it, but there's nothing wrong with PCB. It just has to be very well made. We're going to see. I don't know. But whatever kind of takes up the least amount of real estate, but still has the best sound. That's the direction I'm going to go with it. So in either case, thank you so much. I hope we learned something today, and we'll talk to you again soon. Take care. Bye-bye.